Have you ever wondered what actually pushes continents around? And what really drives tectonic plate motion? Plate tectonics is the theory that explains how Earth's crust moves, forms mountains, opens oceans, and moves continents. When scientists first learned about plate tectonics, they didn't actually know how it happens. And even today, no single model explains how it works. But we do know something, and that is mind-blowing. Welcome to Earth Diary. If you enjoy exploring Earth like this, hit like, subscribe, and tap the bell so you don't miss the next deep dive. To really understand the mechanism of tectonic plate motion, let us picture something simple. How water heats in a pot over a stove. You must have heard about convection. The bottom warms up, hot water rises, spreads out at the top, cools, and sinks again. Now apply the same principle on our Earth. The rocks in the Earth's mantle are mostly solid. But they are hot and ductile, and flows really slowly, in the same manner as the water in the pot over stove. This slow overturning motion is called mantle convection, and it's a major player in plate tectonics. But compared to a pot, our Earth is much more complicated. The mantle isn't shaped like a cylindrical pot, but it is a massive spherical shell. Above the mantle is Earth's entire crust, while below it is the smaller core mantle boundary. And here, the heat comes from not one, but three different sources. First is the heat rising from the core upward, towards the mantle. Inside the mantle, heat is also generated from radioactive decay of the extremely hot rocks. The third one is not a direct heat source, but more of a result of convection, caused by unequal heating. Cooling at the surface, specifically by cold oceanic plates, makes them dense, and so they move downwards and sink. This unequal heating of mantle and crust makes mantle convection an extremely powerful and vast planetary heat engine that drives the tectonic plates' motion. But what is the role of tectonic plates in this? Earlier, scientists thought that plates were pulled along by deep mantle upwelling beneath mid-ocean ridges, just like conveyor belts carry items. But modern evidences changed that. It's actually the movement of plates that causes mantle upwelling at mid-ocean ridges, and not the other way around. So, in modern understanding, tectonic plates are not just passive passengers, like suitcases over a conveyor belt. They play a significant role, as they're part of the convection system itself. Now, what are the actual forces that cause the plate motion? The first one is the slab pull. Basically, it is pulling tectonic plate slab. Cold oceanic slab becomes denser, and sinks into the mantle at subduction zones. And as they sink, they pull the rest of the plate with them. Slab pull is considered the strongest of all the tectonic forces. Geophysical research show that subducting slabs generate about half of the total force that moves tectonic plates. Another important driving force is ridge push. It is basically a gravitational force, resulting from the elevated position of the oceanic ridge. Here gravity causes the lithosphere to slide away from the ridge. Scientific evidence shows that ridge push is a gentler force compared to slab pull. For example, the Mid-Atlantic Ridge is taller than the East Pacific Rise, yet the seafloor spreads more slowly there. Another clue is that faster-moving plates tend to have more subduction zones along their edges. Plates like the Pacific, Nazca, and Cocos move quickly and are actively subducting as well. These observations suggest that ridge push is like a gentle nudge, while slab pull is the real, pulling, force driving most of the action. Another important force at work is mantle drag. That is basically the friction between a tectonic plate and the flowing mantle beneath it. Think about it like swimming in a river. If the current is moving in the same direction as you, and faster than you, it gives you a helpful push. But if the current is slower or flowing against you, it makes your swim harder, acting like a brake. Mantle drag works in the similar way. If the asthenosphere is flowing faster, or in the direction of the plate, it gives the plate a push. But if it's moving slower, or in the opposite direction, it acts like a brake, and resists the plate's motion. There is another force, that is the resistance at subduction zones. Here, the friction between the descending slab and the overriding plate doesn't just generate earthquakes, it also affects how fast the plate can move. When the plates are strongly attached, they slow down the plate motion. On the other side, when the connection is weaker, the slab can slide more easily, allowing slab pull to dominate. So, the speed of subduction is really a balance between the force pulling the plate down, and the friction trying to hold it back. Now, that we've explored these forces, let's take a closer look at what mantle convection really looks like, deep inside the Earth. If you're enjoying the video so far, don't forget to like and subscribe. Alright, back to plate motion and what it all means. Geoscientists generally agree on two main models of how the mantle circulates, that is the giant layer cake model and the deep stir model. Both explains parts of this extremely dynamic system, but neither is completely perfect. As both these models have limitations, so the debate over which model best represents reality continues. The giant layer cake explains that the mantle is like a big cake that has two different layers, dividing at a depth of 660 kilometers. The upper layer is the active, where most plate action and convection occur, while below 660 kilometers lies a thick, slower-moving layer that remains somewhat isolated. This model explains the differences in magma signatures, found at the mid-ocean ridges and hotspots. The basalts from mid-ocean ridge are very uniform, as they are from the well-mixed upper mantle. While hotspot magmas from the deeper plumes, tapping the lower mantle are more primitive and chemically distinct. So, in simple terms, ridge lavas reflect the upper layer of the cake, while hotspot lavas sample the deeper layer. But here is a twist: seismic evidence shows that some subducting slabs can actually go as deep as 660 kilometers, or deeper as well. If that occurs, the two layers would mix. So, while the giant layer cake model explains the different magma aspect, it is not perfect. The deep stir model believes in some kind of whole-mantle convection system, in which the entire mantle mixes as one huge system. Cold slabs sink all the way to the core mantle boundary. Then they melt and rise again, and it continues. Scientists predict that the convection process can mix the entire mantle in a few 100 million years. But here's the problem. If the whole mantle mixes completely every few 100 million years, there should not be any chemical differences between hotspot plume lavas and oceanic ridge lavas. So, this model is also not perfect. Other than these two classic models, there are many recent models as well, that aim to predict the mantle convection. But none can present the real picture of our really dynamic planet. Now that we understand why and how tectonic plates move, how do scientists actually measure their motion? There are many ways that the scientists use to measure plate motion. One is through paleomagnetic signatures on the ocean floor, that records magnetic field of the past Earth like a snapshot in time. The width and age of these magnetic stripes tell us exactly how fast the seafloor has been spreading. Another line of evidence comes from hotspot tracks. A classic example is the Hawaiian Emperor Seamount chain, a nearly 6,000 kilometers long breadcrumb trail left behind as the Pacific plate moved over a mantle plume. It shows the Pacific plate moved about 9 centimeters per year. They also record major shifts in direction, such as the sharp bend that formed around 50 million years ago, when the plate's motion changed from northward to northwestward. Similarly, hotspots in the Atlantic Ocean have scientists reconstruct how continents drifted apart after Pangaea broke up. Today, GPS, satellites, and high-precision receivers provide another powerful way to measure plate motion. To determine how a tectonic plate is moving, scientists repeatedly survey the same site over many years. Calculations from this technology show, for example, that Hawaii is drifting northwest, toward Japan at about 8.3 centimeters per year. Another GPS site in Maryland is moving away, from one in England at 1.7 centimeters per year. GPS measurements are also valuable for detecting small-scale crustal movements, such as the slow deformation that builds up along faults in tectonically active regions. So, if the plate motions continues, then what might our planet look like in the distant future? Utilizing the current trends in plate motions, geologists can predict the future face of our planet. If these trends continue, then in about 50 million years, Southern California will keep sliding north along the San Andreas Fault. Los Angeles could pass San Francisco within 10 million years, and may continue drifting toward the Aleutian Trench. Africa will probably collide with Eurasia, which may close the Mediterranean Sea and form new mountain ranges. Australia will drift north, cross the equator, and eventually collide with Asia. North and South America may separate, while the Atlantic and Indian Oceans expand as the Pacific gradually shrinks. In about 250 million years, geoscientists predict the possible formation of the next supercontinent. This future landmass could form through a reunion of the Americas with Eurasia and Africa, and the Atlantic Ocean might eventually close, while Australia may collide with Southeast Asia. These predictions are fascinating, but they depend on many complex factors. Earth's interior is highly dynamic, and long-term plate motion is difficult to forecast with certainty. Still, one thing is clear: tectonic plates will continue to move for hundreds of millions of years into the future. So, what drives tectonic plates? It is a powerful fusion of heat, gravity, sinking slabs, rising plumes, and a restless mantle that's constantly churning beneath our feet. Earth is alive, geologically, and this fact won't change anytime soon. If you enjoyed this video and learned something new today, hit like, subscribe, and share this video with someone who loves exploring the science of our planet. Thanks for watching and see you next time.